What is up, Flutter devs? Let's start today with a quick recap or check-in with the status of our port of processing over to Flutter. We've successfully ported a whole lot of the API surface. I'd say a majority of the behaviors that someone wants in processing, we have ported over from processing to Flutter. We've implemented it in the Flutter processing package. So let's take an inventory of where we are and where we're going from here. There are a few things left to accomplish in my mind. What we're going to focus on in the near term is there are 2 or 3 categories of properties and behaviors in the processing specification that should be very easy for us to port over. These are like, we have mathematical constants, mathematical functions, and kind of some other behaviors that are almost direct representations of things that are already in Dart to begin with. Now, I wasn't sure at the beginning of this project if I even wanted to create those methods, those behaviors in the processing sketch, given that things like pi and cosine are already available. But at the same time, there's probably a fair bit of processing code out there that has invocations of sine, cosine, tangent, pi, ceiling, absolute value, distance. And wouldn't it be nice if people who already have some of that code don't have to necessarily rewrite that part? Obviously, there are parts that they will need to rewrite or they might need to adjust parameters. But if they copy some code over and the cosine function seems like it doesn't even exist, well, that's a little bit confusing. So I thought, okay, let's go ahead and give processing developers access to the properties and methods that they're used to, unless it would be like totally egregious to do so. Obviously, for example, we are not going to overload mathematical operations that are described in the specification. I mean, like plus, minus, modulus, division, those are literally baked in to how you work with integers and doubles. So we're not going to reinvent that wheel. But I think a number of these methods, it makes sense for us to go ahead and pipe them through so that you can invoke them like you normally would in a processing sketch. So for the next few videos, we're just going to take entire categories of properties and pretty much direct replications of behaviors, and we're going to make them available in the Sketch API. Now, some of those behaviors still will require a little bit of work. For example, I think there's a distance function over here, which is not directly implemented on integers or doubles or anything, so we'll need to create that, but there shouldn't be a lot of that work to be done. But after that, or we'll actually starting with that process, starting with these last 2 or 3 categories of easy porting behaviors, we're going to begin breaking down the definition of the Sketch API into a bunch of different pieces. We're going to start doing that by defining, for example, the mathematical operations, the mathematical functions in its own file as a mixin. And we're going to take that mixin and we're going to mix it into our sketch definition so that anybody who uses a sketch will have access to it, but we can partition it into its own file. Once we do that with the next few videos, we're going to come back in a dedicated video and really start breaking down the big mess of sketch methods that we've defined up to this point. We're going to try to categorize it the same way. We're going to categorize it in directories and files the way that processing categorizes them. That way, we can get to the third area of interest, which is how do we turn this into more of a community project moving forward? Obviously, we don't want me to be responsible for everything forever on this project. We'd like to get more people involved. Well, if we can get the structure of the core sketch definition broken down into pieces, then other developers will have specific areas where they can work without risking the broader project. And it will also be easier, hopefully, to understand how things work when you have responsibilities broken down by directories and files. And the test structure reflects that directory structure and all of those things. These are my focal points for the next however many videos. And then after that, I'm going to return to doing, to replicating some of the code challenges from the coding train and try to put some more creative processing works out there so that people can see more of what's possible with processing and Flutter processing in particular, And then we can kind of go on a bit of a marketing campaign together to let the world know that as long as you're not doing 3D graphics and as long as you're not doing audio, you pretty much have what you need here in Flutter processing. So with that big update out of the way, let's go look at what we're doing today. You'll see here, we're back at the processing specification. And what you see over here on the right side of the screen, let me see if I can zoom in on this. You'll see that we have a whole bunch of calculations here: absolute value, ceiling, constraint, distance, exponent, floor, and down below we have trigonometry. So these are a couple of the categories that I'm talking about where even though most of these behaviors already exist in some fashion in the world of Dart, we are going to expose these methods on the sketch object itself. And that way it should be easier for processing developers to port their code. So let's make that happen. We'll start with trigonometry because there are fewer methods here than there are up in the calculation category. And also probably, just about all of these will be direct call throughs to methods that already exist. So let's go see how we're going to do this. Now, again, I said we're also focused at this point on simplifying or breaking down the structure of our core implementation. So notice, obviously, this is the trigonometry subcategory, but it sits within the math primary category. Let's come over here to our project, and under source in a package, a Dart package, is where your private definitions go, and then you export them from typically a file. A file exports all the stuff that you want users of your package to have access to. But everything under source, that structure is private to us as the people working on the package. Let's create a new directory. We'll call it math. And within math, we will create trigonometry. Did I spell that correctly? Trigonometry. Sure did. Okay. And if actually I spoke too soon, that doesn't really need to be its own directory. Math, we need as a directory, but trigonometry, we just want as a file. So let me redo this. We'll have math. And then within math, we will have trigonometry. Now, I said that what we were going to do here is utilize mixins. The idea is that in core, let's go all the way up near the top of core here. It's a little too far, I think. I'm looking for the definition of a sketch. I guess we are in the definition of a sketch. Yeah, here we go. Sketch right here. Any mixin that we say with something, whatever is defined in something will be directly accessible to any subclass of sketch. Therefore, when we define sine, cosine, tangent in our mixin, we can mix it in with sketch. So let's get the relationship set up right off the bat. We will say, it's been a while since I've defined a mixin. I can't remember if it's a keyword or if it's a class. I think it's just a class, but we'll see if I'm wrong about that. We will call this sketch trigonometry. And let's just stub out a function. We will say double sine, double angle in radians. For now, we'll return 0. Now let's go back to our definition of a sketch, and let's say with sketch trigonometry. Okay. Now, wherever we subclass a sketch or invoke something on a sketch, we should be able to invoke this sine method. So let's see if I can just show you this compiling. Let me open up our main example. We won't bother running it for right now. I just want to show you what I mean about invoking it. So I'm just going to go to a random place here where this is the definition of a sketch where we use callbacks. And in here, anywhere I want, I can say S for sketch dot sine. And so even though we didn't define the sine method on the sketch itself, because we mixed it in, we can invoke it as if we defined it within the sketch. This is going to be our primary tool for breaking down our big, massive core definition for a sketch. But again, for now, we're not breaking it down yet. For now, we are just implementing some new categories as mixins. Now, let's see. What do we want to actually implement here? Coming back to trigonometry, we have sine, cosine, tangent, then a sine, a cosine, a tangent, a tan 2. Let me just declare these. Actually, we can probably just implement them directly. So let's import math. Import, is it Dart math? And we're going to say as math because we're going to have some name conflicts here. So math.sine angle in radians. Now let me see if, okay, so degrees and radians, these are two different modes. So here's the problem we're going to run into. Let's see where, whoops, uh-oh. I think I just removed, oh, there it is. Okay, so where is sine? Here's sine. Here's what we need to contend with. Let's see. Calculates the sine of an angle. This function expects the value of angle parameter to be provided in radians. Okay, that's interesting. So I need to see, maybe I misunderstood what a couple of these methods were doing. What is this? Okay, this is a conversion method. So in some areas of processing, there are methods that set the future interpretation of values. I thought that calling degrees would cause all of processing to interpret all future angles as degrees instead of radians. That's not the case. It looks like degrees really means, what this really means is radians to degrees, but it's just called degrees as a shorthand. So that's fine. This implementation right here is actually all that we need. So we can do the same. We can come and say cosine angle in radians, return math cosine angle in radians, and then tangent angle in radians. And then we want arc sine, which is a sine. Let's see, what should we call? I mean, that's just a fraction, but let me see. I don't know what that parameter is typically referred to. They're just calling it a value. Okay, fine. Double value, return math dot arcsine value. And let me do something that's going to make this easier on us. We're going to take in a num. You know all those places that I keep having to write to double everywhere? Well, num is a type that includes both integers and doubles. So then you can pass in an integer here and it's not going to complain about the type. All right, we also want arc cosine. And we want arc tangent. And then there's a second version of arc tangent, which I believe it's dy, dx, dy, or dy, dx. Let me see what the order that processing takes these in. Y and x, okay. So we will say num y, num x, return math a tan 2 y x. And I believe it's the same order for Dart, but let me make sure. Turn it between the positive x and the vector BA, the vector BA. And what's the order of vectors? Vectors are x comma y, therefore A is y, B is x. So we are good. A tan yx. All right, what else do we have here? Degrees and radians. Okay. I'm going to define that up here at the top because I think these will be more commonly used. Double degrees. We will take in angle in radians. How do we return. Let's see, what is this complaining about? Oh, I just haven't returned anything yet. Okay, so how do we convert degrees to radians? We take, or actually, how do we convert radians to degrees? We will take angle in radians divided by 2 times pi times 360 degrees. This first part is the fraction of a circle based on radians, and then we multiply it by the number of degrees in a circle. Double radians, which we'll take in degrees. We will return degrees divided by 360 times 2 times pi. Now there's something else that we can do here that technically will remove, I mean, it really is not relevant for performance, but we could technically, I think, reduce the computation here because what we're dealing with is ratios. We could say, for example, angle in radians divided by pi times 180 degrees. Those are the same ratios, but we remove the multiplication by 2. And similarly down here, we can say degrees times, or degrees, divided by 180 times math.pi. Pi radians is 1/2 of a circle, 180 degrees is 1/2 of a circle, in terms of sweeping angle, obviously. Okay, so I think that is everything there, right? We've now technically, just like that, implemented the entire trigonometry subcategory. Now, interestingly, some of these things have tests, or, well, for us, they can be tests, but they have visual examples. And you know that whenever possible, I like to replicate these visual examples. So let's see if we can do that here. Let's open up our project structure. Let's go down to our tests in the package. And let's create a directory for math. And then let's say Dart file trigonometry test. And let's just copy one of these other groups of tests. This is going to be math and then trigonometry. And then I think, what are we testing over here? We're testing tangent. Now I'm going to get rid of all the other tests in here. We'll just start with one and then replicate it for the few others that have tests. I think that matches up. And this is going to be math, trigonometry, tangent, like that. And then let's see what this code says. We'll grab this code. We'll come into the draw method here. We are not going to draw a circle because that's from the old test. We want to keep no loop because we don't want to animate. That'll keep our test from completing. Now let's port this code. We will say final A, actually not, it's not final, double A, double inc, which stands for increment. Okay, now here's something we didn't put in there yet, but we should. So C2 pi, in this case, it should actually be S.2 pi, but that's a constant that's defined by processing. Let me go see, forget where those are. Those are under constants. Okay, so let's also add those as well. Now, constants are its own category. So we'll follow up. We could put that in its own file, but to avoid any confusion, let me create a directory called constants, and I will also create a file called constants. And by the way, these files, I believe they should begin with underscores, I think, to indicate that they are not public. But what we Now, I was going to say we want to export it from Flutter processing.dart, but actually I don't think we need to because we're already mixing the APIs into the sketch. Under constants, what constants do we want here? Well, first let's say sketch constants. Okay, that's where we're going to put the constants. Now let's go to core. And now not only do we have sketch trigonometry, but we're going to mix in sketch constants. Now we have two mixins, and you can see how we keep adding more and more mixins. Under constants, we want pi, half pi, quarter pi. Half pi is pi divided by 2. Quarter pi is pi divided by 4. And then we want tau and 2 pi. Well, let's start with 2 pi. And then we have to figure out what tau is. Let's go see what tau is. Oops, did I click the wrong thing? I think I did. Okay. Tau is a mathematical constant with the value of this thing. It is the circle. It is the circle constant relating the circumference of a circle to its linear dimension, the ratio of the circumference of a circle to its radius. It is useful in combination with trigonometric functions such as sine and cosine. Well, if they say so. Okay. Now this is going to complain because we're using processing capitalization. I'm going to suppress this. I'm going to suppress it for the file, except I can't remember what the syntax is for that. Let's go do a search. This is Dart analysis options ignore for file. Enabling and disabling, individual rules. Here we go. Ignore for file. There. Okay, now no more analyzer complaints. Let's save that. Come back to this test. Now 2 pi is resolved. Line needs to become s.line. And then we need to actually pass in offsets for this instead of just a bunch of properties. Or a bunch of arguments, I should say. And then, can I make that a double? Okay. Now everything compiles. And the question is, will this golden file look more or less like the tangent example here? Let's find out. Flutter test update goldens plain name equals tangent, and this is going to be test math trigonometry test. Well, it says it was successful, but where are the goldens? There they are. Okay. Well, once again, we have issues with specifics around how lines are rendered, essentially. Clearly, it's not as precise with what we're getting out of Flutter versus what we get here from processing. That's not a problem related, I don't think, to what we're doing here. This is a recurring issue. Maybe at some point I'll figure out there's a flag that we can pass that gets us slightly more accurate rendering or changes the anti-aliasing logic or whatever it is that's causing this problem for us. Nonetheless, what you can see definitely is the same waveform. So as far as I'm concerned, that's a successful test. Let's see what else we have here. Here is sine. So let's test sine. Call the file sine, call the test sine, copy the code over. A is double, increment is double, gonna rename you to increment. Also, A is for angle, and it's angle in radians. There are no extra points here for avoiding variable names that make sense. Angle in radians. And then I we're going to make into a double so that we can say offset, the starting offset of the line, the ending offset of the line. Save that. And now we're going to run the test again, except this time we're going to run sine. And there's sine. And now this time the spacing worked out for whatever reason. I guess more space, fewer lines are being drawn, so there's more space between them. But there we go. That's sine. What else do we have here? Here's cosine. Let's implement that one. Change the name of the test to cosine. Change the name of the file and then the name of the test, both to cosine. Now let's copy this code. Angle, you're a double, increment, s.2pi, blank line to match the others, change I to a double, s.line, offset, and offset. Save, run the test. And there's cosine, which matches pretty much what we're seeing there. Close enough. Okay, do we have any other visuals? No. Okay, well, let's wipe these out. Let's get rid of all of these tabs to make some space. We've implemented these, and the ones that have visual tests, we have tested visually. Now, interestingly, tau itself seems to have a test. So let's test that, but let's also see if any of the other constants have visual tests for some reason. And they do. Actually, these are all the same test. These are all drawing the same thing. They're using all of the constants. Let's test these. In our test directory, let's create a new package called constants, and then we will create constants test. Let's copy our test from math. We will call this constants test, which is, well, overwrite the one we already created. And now this is, the group is constants. There is no subgroup, so I'm going to get rid of the subgroup here. I'm also going to get rid of 2 of the 3 tests because we only have one golden file to draw here. And this is going to be just constants is the name of the file. Constants is the test name. Although, yeah, I guess that's, I mean, it's constants. Constants doesn't tell us much. Maybe it's nice to put the constant names in there, but there are a number of constants. Let's leave it like that. That's fine. All right, let's take this code here. Let's copy it over. you're going to be s dot width divided by 2, s dot height divided by 2, s dot width. And these look like these are all final. I don't think they're changing here, so we'll make them final. And then we want, oh, we don't have arc. That's going to be a problem. So we actually can't write this test yet. So what I'm going to do is say to do, bring back when we have arc support. And then we're just going to comment it out. So when we implement arcs, whenever that happens, we'll come back and make this test possible. At least I think we didn't have arc, right? We do have arc. Oh, okay. What I was thinking of was Bezier curves. That's what we don't have yet. We're missing Bezier curves. Okay, so false alarm. We just need the parameters to be correct here. So arc requires an ellipse, a start angle, and an end angle. So what is our ellipse here? So s dot arc, ellipse, and what are they passing in? I think we want ellipse from center with radius. The center is x comma y. The radius 1 in this case is d and d again. So the first one's a circle. Actually, they're all circles. They're just smaller and smaller circles. So hold on, we might be able to make this with less detail then. Ellipse from center, width and height, center with radius. It's going to be the same amount of information either way. Start angle is going to be 0 and then quarter pi. S dot quarter pi. Quarter pi is one of the constants that we're testing here. Okay, so that's the first arc. Then the second arc has, I'm passing these in as radius. That's going to be a problem because these aren't the radius, are they? These are, well, that's the weird thing is well, let's go see what the definition of arc is. It's kind of weird that arc is taking in the diameter, but maybe it is. Okay, width and height, and the width and height will be diameter. So let me change this from over to center with the width and the height. Width, height. Okay. So that's the first ellipse. The second ellipse is similar. The diameter, we have a minus 20 on the diameter. And then the end angle here is half pi. Then we want minus 40 on the diameter. And we want full pi, which is half a circle. And then lastly, we want this tau thing. We're going to go minus 60 on the diameter, and then we want s dot tau. Okay, let's save that. Now we're going to say the test is called constants, and the file is going to be test constants test. Let's see what we get. Okay, well, not quite what we were expecting. Let's see. So the question is, why are we getting the sector that's drawing way out here to the edge? because I still have one incorrectly specified ellipse. In fact, I think I have an extra ellipse, don't I? I don't even think this one should be here. Let's try this one more time. All right, now we have what we're looking for. So I guess tau, not really sure how that works then, because these first three are clearly operating on angle values, but I thought tau was some kind of ratio. The constant relating to the circumference of a circle to its linear dimension. Oh, whatever. I guess the question is, what's the difference between tau and 2 pi? I don't know. Here's the value for 2 pi, 6.2831855. Go back to tau, 6.2831855. They're literally the same value. So I guess they're just domain. I guess tau has a domain-specific meaning in mathematics, and it happens to be equivalent to 2 pi, which is a full rotation around a circle. Okay, let's close all that down. Where are we now? I said today we're going to try to get all of math. So you've seen how we're approaching this. Now let's see if we can power through the last subcategory. So we're not going to do bitwise operations. Those are literally baked in to the Dart number manipulation system. We're not going to do operators for the same reason. I think p-vector, maybe I'll come back in another video and do p-vector. Probably a little bit too much for us today, but I think calculation we can do. So I'm going to try to select all of these if I can. Copy those. Let's come back in here. Let's come back up to our math directory and let's create calculations. Class sketch calculations. I'm going to paste these in here. Absolute value is going to return a double from a num, I think. Ceiling is a double from a num. Again, number could be either a double, a floating point, or an integer. Constrain, I don't know what the API is on that. Let's see. Constrain. The value, minimum, maximum. So it maps to clamp. Let's go ahead and just implement these as we go. Return value dot absolute value. Is that only defined on doubles? Let's return a num. Return value dot ceiling. You will return an integer, because if you are calling ceiling in concept, what you are doing is saying, give me the integer which is higher but closest to my current value. So it is inherently an integer, though you can cast it back to a double if you want. Here for constrain, we will say, we will return a num, and we will take in a num value, a num min, and a num max, and we will return value.clamp min max. Dist, let's go see what's up with dist. Calculates the distance between 2 points. Okay. Well, in this area, I'm going to keep things, I think, actually, well, I was going to say keep it the same way processing has it, but we can't represent both of these at the same time. So I think we're going to have to go with offsets. For now, let's just support. Let's see, what do we want to do? We'll return a num, and we will take in 0.1 and 0.2. We will return, let's see, we want to import Dart UI, sure. P2 minus P1 dot distance. Let me see, distance between 2 points. This order shouldn't matter, I guess, because distance is going to take a positive. It's going to always be positive. All right, let's see what we're doing with exponents here. Returns Euler's number raised to the power of n. So it's e to the n is what this means. I guess technically we can return a double here because there's no way this evaluates to something other than a double. And we will take an int n and we will return, I don't know if e is defined. I guess it is. And is there a pow? Let's see. Power e to the n, I think is probably what we want. Oh, let's see what this says. Oh no, that's our power. Okay, to avoid name conflicts, we need to call this math. This will be math.e and math.power. I guess that returns a num, so we should too. Returns x to the power of exponent. So this should be e and this should be our exponent. Now what's it complaining about? I guess we can call that a num. Okay, then we're good. All right, so that's exponent, e to the whatever. Floor. We can return an integer. Floor is essentially the opposite of ceiling. LERP stands for linear interpolation, but let's see what the specific arguments or parameters should be for this. Start, stop, amount. So between these two values, we're going to apply that percent. I think we can return a num from start and num percent, and we will return. Okay, actually, we don't want to return a num here because what we want is double dot, or sorry, lerp double start end percent, which means we need to return a double. And for some reason, this returns a nullable type. Why are you nullable? I'm just going to assume that it's non-null because there are weird cases where that's a complaint. Okay, and apparently percent needs to be a double. Logarithm. Calculates the natural log of the given value. So we will return a num, we will take in a num, which is n, we will return math dot, this is natural log, right? Natural logarithm of 2. I think that's what we want. Oh, that's a value. What do we have in terms of methods? Okay, here, so I guess Same name. And then magnitude calculates the magnitude of a vector. So we will return a num, I think. We'll see if that works out. We will take int x, int y, and then optional int z. Now, if it's just x and y, then all we need is, we can just use an offset and ask for the distance, which is similar to what we have up above. With z, I don't remember what we want to do to the math to get the distance in 3 dimensions. Just add one more piece to the equation. So we can return math.square root of, this formula is between 2 points, x2, x1, y2, y1, z2, z1. Distance, if we're asking what is the distance of a vector, the second point is just 0, 0, or 0, 0, 0. So it's x minus 0, y minus 0, z minus 0. And so what we can say is math.power x2, so this is x squared, x minus 0 squared is x squared, plus math.power y minus 0 squared is the same thing as y squared. And then we will say math.power, what we will do here actually is we will say equal to 0 by default. So we will say z2. And then that should be the distance of a 2 or 3 dimensional vector or point from the origin. All right. What are we mapping in map? Remaps a number from one range to another, which is essentially what linear interpolation does, by the way. In the first example above, the number 25 is converted from a value in the range 0 to 100. All right, here's what we're going to do. There may be a more efficient way to do this than what I'm about to do, but I think what I have in mind will work fine. So we're going to say value start 1. We'll say domain start, these don't need to be ints, double value, double domain start, or perhaps domain min, double domain max, double range min, double range max. And then what we can say is percent sorry, let me think here. Percent is domain max minus domain min. It's going to be value divided by that. That's the percentage between the min and the max. And then we can return the linear interpolation of range min, range max with the percent that we just calculated. I think that should work. Probably should write some tests for some of these, but I'm not going to today. Maybe some other time. Max, let's confirm what this means. First number, second number, third number, or a list. Okay. Well, the question here, challenge here is, how do we do the best we can to replicate this, knowing that we can't overload methods? For handling 2 or 3 parameters, that's straightforward. We can just make C optional, but then there's no way to handle the list. I think I'll just create a second method called max list or max in list. So first we'll have max, and it will take in A, B, and then these should be nums again. Optional C. And then, let's see, I don't know what the most concise way is to get the max. I mean, there is already a math dot max between A and B. Actually, we say return C is not equal to null. We'll return the max we just calculated. Otherwise, we will say math max, max, and C. Oops, I have that backwards. Okay, and then we can say max in list, and we can take a list of num. And here, what we are going to do is fold. We're going to say list, I think it's fold, initial value. We can say list.first. What fold does is it runs a function for every single item in a list, and it tells you some previous value that you're holding on to, and reports the new value. And for us, we just want to go down the list and remember the largest value. So we're going to return max between, let's call this one previous max. So we want the max between the previous max and the new value. And what we get out the other side will be the max. And here I'm going to put assert list is not empty, because it makes no sense for you to ask for the max in a list where there are no values, because then there is no max. Min, let's kind of do the same thing for min here. Min, rename this to min, math.min, math.min. Min in list. We want this to be previous min, and then we want math.min. Okay. Norm is going to be some kind of normalize or normal. Let's go C. Normalizes a number from another range into a valid value between 0 and 1, identical to calling map value low, high, 0, 1. Well, then that's exactly how we're going to implement it. Returns a num, takes in, 3 parameters? Value, start, stop, num value, num start, num stop. And we're going to return map value, start, stop, 0, 1. Let's see, did I say those had to be doubles? That one doesn't have to be a double. That one doesn't have to be a double. I don't think any of these had to be doubles. All right, now norm is implemented. Now let's look at pow for power. Base of the exponential expression, power by which to raise the base. So we're going to say, so it's going to return a num, and we're going to say num base, num exponent. I'm not calling it E because I don't want to confuse the actual number e in mathematics. In fact, let's go all the way to exponent. All right, round. We'll return an integer because rounding inherently takes one value and rounds it to the nearest integer. We will return value dot round. And then what's the difference between sq and square root? So square is a number. Okay. All right, and then square root. I guess there are some. I guess if you are already a square of something, then you might be an integer when you're returned. So we can return a num, and we will return math.square root of value. All right, save. And that is all of the calculations. Now, did we mix that in yet? Sketch calculations. Now we have three mixins. We have the mathematical constants, the mathematical calculations, and the trigonometry. Now you can see how we are composing, not in the widget tree sense, not in the runtime composition sense, but at compile time, we are composing our definition for a sketch. And eventually we're going to break down a bunch of this nonsense into pieces that we bring as mixins as well. It's going to get a little more complicated with some of those. But we've now gotten rid of all of these math APIs. Let me see if I can close all of these, close that whole group. I think p-vector we'll come back and do in a dedicated video because there's a bit more to it. But beyond that, what else am I thinking about here in terms of categories? I can't remember which category I have scheduled for the next video, but I can't remember now. I don't know. There's one or two other major categories here that we can essentially do the same thing, and we will, because we can knock those out quickly like we did today, and then they're done. Don't have to worry about them anymore. So I think we have 1 to 2 more videos where we do this same kind of thing. Then after that, we're going to refactor. We're going to break down our core definition into many pieces. We're going to talk about defining a kind of base painting context that will allow us to define some of those painting related behaviors on top of it so that we can break it apart. And then what we'll do is probably put together a contributing guide for the repository. We might expand the README file a little bit. We'll clean up some of the testing tools so that it's easier to write some of these tests. And then the project is kind of ready for other people to get involved. And at that point, the videos coming out after that will be mostly around, hopefully, creative coding, actually using this thing for coding challenges, as well as various projects of my own. So that's what's coming in the future. I hope you learned something today. I hope you see the direction that we're moving. I hope you're getting excited for us kind of almost being at the MVP milestone for this project. I'll see you in the next video.